PiC, a phrase in context dataset for phrase understanding and semantic search, work done by Thắng Phạm, Xuân Yun, Trung Bùi, and Anh Nguyễn. In this work, we are excited to share PiC, a new benchmark for testing NLP models on phrase understanding and search. PiC consists of 3 tasks: predicting similarity of 2 different phrases in the same context, finding a phrase similar to a given query phrase, and finding a phrase that matches the query more from one of 2 contexts. Variable-based models demonstrate similar capability to humans on finding a phrase in a natural text, yet they score far below humans on the 2 harder tasks of discriminating phrase sense of PS and PSD. Interestingly, our benchmark is still unsolved for the latest GPT-4 as of April 2023. Given 2 sentences that contain the same phrase massive figure, are the phrases green and blue massive figure semantically equivalent? No, they are not. The green massive figure refers to a huge physical model, while the blue one means a giant number. Therefore, they are not semantically equivalent in the given context. The same phrase may have multiple meanings given different contexts. Why phrase in context? Understanding phrases is a key to learn new vocabularies, disambiguation, and semantic search. State-of-the-art models mostly capture the common meaning of the phrase without strong dependence on its context. No human-verified dataset for phrases with context. Existing phrase similarity benchmarks contain around 38 to 99% lexical overlap. Those drawbacks are limiting the evaluation of phrase understanding. To prepare data for annotation, we conducted a 6-step procedure to collect all possible polysemous words, starting by downloading all wiki articles in a dump file and removing around 9.51 million empty articles to obtain 6.27 million articles. Next, we use PiC, which is an NLP library for extracting around 286.78 million noun phrases. We then remove a phrase if it only appears in one sentence, since they have zero chance of being polysemous. Next, we leverage a set of polysemous words from word in context dataset to retain only phrases that contain at least one weak word. The same phrase in 2 dissimilarity sentences or domains is potentially polysemous. Thus, we use the state-of-the-art sentence similarity model to rank pairs of 2 sentences by semantic and domain dissimilarity. In the last step, we remove erroneous phrases and take the top 19,500 triplets of phrase document D1 and D2 for annotation by linguistic experts. Data annotation and verification. For data annotation, given 2 pages that contain the same phrase massive figure, we ask an annotator to read page 1 to understand the meaning of the green massive figure and rephrases, and then repeat for the blue massive figure in page 2. We also ask the annotator a yes-no question to confirm whether the target phrase carries different meaning in 2 pages. There are 2 routes for verifying annotations. The first one is done by around 1,000 qualified freelancers from Amazon Mechanical Turk. Those examples rejected by the freelancers are checked by another set of file writing experts in the second round. Benchmark and statistics. The first task is phrase similarity, or BS, is the binary classification task. Given 2 phrases with the same context, the model predicts whether these phrases are semantically equivalent or not. To create a positive example, we extract the sentence that contains the target phrase massive figure from page 1 for sentence S1. For sentence S2, this is similar to S1, but the target phrase massive figure is replaced with its paraphrase, which is huge model. The negative example is similar to the positive one, except for the phrase in S2, here giant number, which is the paraphrase of massive figure in page 2. To make sure the paraphrase of the blue massive figure, which is giant number, is not semantically equivalent to the green massive figure for the negative label, The label from the annotators for Q3 must be a no. We also enhance the quality of BS dataset by an extra verification round for verifying both negative and positive examples. In the second task, phrase retrieval to create a context basis for BR bus, we extract 5 sentences before and after the sentence that contains the green massive figure as an answer. The query is huge model, which is the paraphrased version of massive figure rephrased by the annotators. PR page is similar to PR bus except for the longer context, which is the entire wiki page. For the PSD task, we combine two 11-sentence passages from page 1 and page 2 to form the context paragraph. If the query is huge model, the answer must be the green massive figure. In case the query is giant number, the answer must be the blue massive figure. For statistics, PS, except turning on other datasets contain a large percent of instances with lexical overlap. Average phrase lengths are comparable. And PS contains only noun phrases, the most common type for semantic search data from Yahoo. For PR, the dataset size is around 3.5 times smaller, but the paragraph document length is around 2 times longer. For PSD, it has only 5K examples, but it's quite challenging. Experiments and results. For experimental setup, following Yu and Ettinger, we computed non-contextualized phrase embeddings by fitting a phrase only to the model and compute the average pooling of the phrase words. Similarly, for contextualized phrase embeddings, we fit the whole sentence containing that phrase to the model and compute the average pooling of the corresponding phrase words. With this approach, the phrase words have more information from the surrounding tokens. We did experiments on different models categorized into 4 groups: phrase level, sentence level, contextualized phrase embeddings derived from contextualized word embeddings, and trend span selection models. There are 2 main approaches for our experiments. For the non-training approach, we use similarity-based ranking to measure the equivalent semantic of 2 phrases in different contexts. With training, we fine-tune the span selection models with different transformer-based models as backbones. And we found that in BS task, incorporating context into phrase embeddings improve accuracy. Without context, all models perform at less than equal to 50% accuracy. However, incorporating context into phrase embeddings substantially improves mean model accuracy for both approaches. PS requires the models to rely on context. There are 3 main groups for human study: Group 1 with 20 graduate students, Group 2 with 5 experts without training, and Group 3 also with 5 experts with training. The best human performance on PR tasks is 95%. The best machine accuracy from span selection model is 94.28%, which is near human performance. Deep models perform at human level on PR tasks. For PR, in ranking, context only has word-based embeddings, but not order, since incorporating context sentence hurts their accuracy. Top 1 accuracy for non-contextualized and contextualized embeddings are substantially lower than non-expert baselines and human upper bound. There is still room for improving encoders to capture contextualized phrase embeddings. PR-pass trained span selection models perform impressively at near upper bound level, 93 to 94 exact match. On PR page, NS models exact match only drops slightly to 85 to 89%. For PSD, PR-pass trained span selection models frequently find one occurrence of the target phrase, but mostly located in the wrong context passage. That results in the significant drops up to 41% when the location of the predicted span is taken into consideration. Interestingly, the latest GPT-4 as of April 2023 outperforms word-based models, for instance, scoring 75% on phrase similarity compared to 69% of bird-based models, yet it still underperforms the upper bound of 93% set by human NLP experts. We found a similar conclusion on PSD. The details of limitations, human study, and training, as well as qualitative examples, can be found in the paper. In sum, we propose PiC, which is the first human annotated benchmark for training and evaluating contextualized phrase embeddings. PS is the first required models to rely on context. PR is the first QA-style phrase retrieval task. PSD is the first phrase and disambiguation task. Span selection models reach near-human accuracy on PR but perform poorly on PSD. Contextualized phrase embeddings derived from untrained word-based encoders or span selection trained models yield poor accuracy. This research was funded by National Science Foundation, Auburn University, and Adobe Research.